Hello, we are Team 30. We have implemented a mini research on the field of natural language processing, specifically classifying toxic comments. Today, online platforms such as social media have enabled individuals to share their opinions with other people around the world. While this has brought upon countless benefits, it also created a problem, which is toxic comments. It is a sad truth that some people choose to attack other people online by posting malicious comments. Since comments can also be made anonymously, it becomes even harder to stop individuals from making toxic expressions. What if deep learning can be used to automatically classify toxic comments so that they can be filtered? Not just toxic comments, but text classification in general has been a classic application of deep learning in the field of natural language processing. Our team has therefore decided to experiment with different models to see how effectively they can recognize comments and label them into different categories. We will also look for ways to improve the level of performance. In this slide, I will briefly introduce the 4 categories of models that we have implemented throughout this project. The first 2 networks are convolutional neural network and recurrent neural network, which are standard networks that are frequently used in deep learning. The third model is convolutional recurrent neural network, which combines characteristics of both CNN and RNN to form a new type of network. Finally, we will use BERT model, which stands for bidirectional encoder representations from transformers, which is a language representation model developed by Google. Detailed mechanisms will be discussed in the following slides.
The first architecture that we wanted to utilize is CNN, the convolutional neural network. Its usual application is usually on image processing, where a convolutional network reduces data into a form that is easier to process with the use of shared kernels or filters that slide along input feature and produces feature map. It involves convolutional layer, pooling layer, or fully connected network, and etc. However, recently it expanded its application as recent studies showed that CNN can also be successful in natural language processes, which used to be dominant study with recurrent neural networks. So in this project, we will see if CNN can show a successful performance when processing natural language in our toxic comment classification model.
Next, I will explain the mechanism of recurrent neural networks. In recurrent neural networks, each word of a sentence is treated as a separate input occurring at some time t. The activation value derived at time t minus 1 is also used as an input at time t, thereby creating feed-forward structure. This means that dependencies between data points are taken into consideration. The figure on the slide shows that recurrent neural networks have a feedback loop which acts as a memory that can store information from previous inputs. There are several limitations when using a simple recurrent neural network. The first problem is that it can capture dependencies in one direction of language, but not the opposite. This implies that the word coming after does not affect the words coming before, which isn't true. Another problem is that simple recurrent neural networks also find it difficult to capture dependencies that extend to long-term periods, and it also experiences the vanishing gradient problem. If this happens, then the values of a gradient become so small that the model stops functioning properly. So what is the solution? One way to solve the problem of single direction dependency is to use a bidirectional network. This type of RNN has both a forward and a backward neural network, which means that inputs from future time steps can be used to modify the network's accuracy. LSTM stands for Long Short-Term Memory Network, which is often coupled with recurrent neural networks to solve problems in natural language processing. The figure shows that there are gates which decide whether to delete or store new information based on the weights assigned to each and every word. This enables the network to store information that is important and forget other information. Combining the bidirectional structure and the LSTM architecture, a neural network such as the one shown on the slide is created. This is called bidirectional LSTM recurrent neural network and is a much more sophisticated network than the simple RNN. As this network contains the benefits of both bidirectional and LSTM networks, its performance will be expected to be far greater than that of a basic recurrent neural network.
CNN, on the other hand, as you can infer from its name, is a mixture of CNN and RNN. Usually the structure involves front end as CNN and back end as RNN. It is widely known that the benefits of CNN in NLP field is that CNN can capture features and RNN can process data in sequential order. Like as you can see in this figure, if you have this Photoshop of text, CNN can change it into text data, and the RNN can process the text data and give you the results you want. However, in our project, we will not involve Photoshops and making Photoshop into text data. So we will just use the convolutional layers directly to text data. So it could capture feature from the text data itself and give it to RNN layer and process to get the results we want. So also we will see if CRNN gives better performance compared to CNN or even RNN models.
The final topic to discuss is the BERT model. It is an open source framework that helps computers to understand ambiguous language and sequential data. While conventional networks such as RNN and CNN follow a fixed order of processing data, BERT has no such restriction. It is intentionally designed to read in both directions at the same time. The key idea of BERT is the application of a transformer, which is an attention mechanism that can learn contextual relationship between words. Here, attention means that weighting between words are dynamically calculated based on their relations. As opposed to directional models, the transformer processes an entire sequence of words at the same time, which allows the model to capture contextual information of a particular word, based on all of its surrounding words. BERT model is trained on two important tasks in natural language processing: masked language modeling and next sentence prediction. In masked language modeling, the computer predicts a hidden word based on its context. Next sentence prediction involves two sentences which are placed side by side but separated using a token. This can be seen on the diagram on the slide, where sentence 1 and 2 are divided by the token SCP. It attempts to predict whether these sentences have a logical connection to each other, or if they are grouped purely by random chance. The power of BERT model is that these pre-training stages act as a knowledge base, and the model can then be applied to a wide variety of tasks by fine-tuning parts of the core model to adapt to the problem.
So in the result analysis part, I will briefly go through the architecture of each model that we have. Briefly speaking, we have CNN, RNN, CRNN, and BERT model. Each of them is tuned with the hyperparameter tuning and architecture modifications and brought out the best models of each category. So moving on to CNN first, we have three different depths of CNN, one in one layer, another in 2 layers, and the other in 3 layers model. And for RNN, we use LSTM layer or bidirectional LSTM and compare if there are any difference between those two models. Third, the CRNN model. One CRNN model will involve LSTM layer, which will be used after convolutional layer. And the other model will involve bidirectional LSTM model, which will also be followed by convolutional layer. So we will see the CRNN model with LSTM and CRNN with bidirectional LSTM could give a good performance or not. And lastly, it is the BART model, which will be later explained by our teammates. So first of all, the single layer convolutional neural network. It involves some convolutional network here, and it has max pooling, embedding, dense, and dropout layers to give out the best performance it could give. All the models are trained under the optimizer Adam under the Epoch 2. The validation AUC score of one layer convolutional neural network is 0.9689, and the validation loss is 0.0596. Next, convolutional network with 2 layers of convolutional 1D layer. It also has max pooling, dropout, dense, and etc., which has AUC score of 0.9807. The convolutional neural network with 3 layers of convolutional 1D, it has much more depth, but as you can see, the validation AUC score got even less than the convolutional neural network with 2 layers of convolutional layer. Now the RNN. This RNN model used LSTM layer, as you can see here, and it also involved dropout, pulling, and dense layers. Its validation AUC score was 0.9814. Next, this RNN model involves bidirectional LSTM layer along with pulling, dense, dropout, and even convolutional layer so that we could enhance the performance. The validation AUC score here is 0.9827.
Next, we use the CRNN model. For the first model of CRNN, we use convolution 1D layer with the LSTM layer from RNN. We can check the detailed model with the schema in the right. The recorded AUC score is about 0.979 and the loss is about 0.0496. Next, we use the convolution 1D layer with the bidirectional LSTM layer from RNN. We can check the detailed model within the schema in the right, and the AUC score is about 0.982, and the loss is about 0.0498. Lastly, we use the BERT model with the PyTorch linear model. The average AUC score is about 0.9889 among the 6 columns, and the loss is about 0.0340. In summary, we trained 8 models within 4 types: CNN, RNN, CRNN, and BERT. Finally, we compared the AUC scores and loss with accuracy, precision, recall, and alpha score additionally. We can find that the RNN is better than the CNN models when we compare the AUC scores. Also, we can find that BERT is the strongest model used in our project among 4 models by comparing the many scores that we used in the result.
After training, we test the model with test dataset that was given by Kaggle. First, we check the RCUC, which means that if the area under the curve becomes closer to 1, it means it has high accuracy. These 6 figures mean toxic, severe toxic, obscene, threat, insult, anti-hate, respectively. BERT model's curve was similar to ideal case, and its value are bigger than 0.9, so we can consider that it was a great model. And the one layer CNN doesn't make good result, it has even under 0.5 values. 2 layer CNN model is similar to previous one. Most of them are bigger than 0.5, but it is still close to 0.5. 3 layer CNN was similar to the previous one, and CRNN, which has LSTM layer, didn't work well. There were some values under 0.5. CRNN, which has bidirectional LSTM, was same, and the AUC of RNN model was quite high. Most of them are greater than 0.9 and close to the ideal case. Both of LSTM model and bidirectional LSTM model were good. LSTM's result was slightly higher than bidirectional LSTM model. The result of BERT and RNN were reasonable, so we reconnected these 2 layers. The result was still high. Sum of categories becomes higher. Comparing the curve of the models, RNN models are much better than the others, and the LSTM model shows the best performance. These are the confusion metrics of each model. Based on these values, we can calculate AUC, recall, and F1 score. The darker the blue, the higher the probability it means. Intuitively, RNN structures have high true positive and false negative probability, and they have low true negative and false positive probability. So we could expect that they would show great performance. The confusion matrix of BERT plus LSTM implies they would make high performance too. And the left figure on the slide is the recall box plot, and the right figure is the F1 square box plot. We can easily check BERT and RNN model have high scores, especially for BERT plus LSTM model has the highest score, so we could think that this machine learned very well. We also draw the bar graph of the performance of each model across each category. Thus, we could compare the result of each category of each model easily. BERT models scores are all high, so we could notice that BERT is a very powerful method for NLP. We could find out the one-layer CNN structure is not stable, so we consider this model is not suitable for our purpose. The other CNN model result very high score with some categories, but AUC is still low. We can see that CRNN with LSTM model is not a good model. The result of CRNN with bidirectional LSTM model is like this. You can check that the result of RNN models are quite high for all categories. Thus, we can conclude that the RNN structure is suitable for our purpose. Based on the result of test dataset, we found out that RNN-based models show very high performance, so we wanted to compare in detail by numerical values. The table on the slide is the score of each label of each model. Comparing the scores, RNN LSTM model is slightly better than RNN bidirectional LSTM model. Also, we compared LSTM model and BERT plus LSTM model. BERT plus LSTM model is slightly better than LSTM model. And we compare BERT model and BERT plus LSTM model. Recall score was very similar, but for overall, BERT model is slightly better than the BERT plus LSTM model. And finally, by taking average of each model, we choose the best model of our test. BERT shows the highest score, so we conclude that the BERT model is the most suitable for our task. In conclusion, we applied 3 scores, AUC, recall, F1 score, but 3 of them didn't show the same tendency. For CNN and CRNN model, AUC was bad, but recall and F1 score were not that low. Therefore, we showed that we should check various scores for higher reliability. And as a result of our test, we could check RNN is better than CNN for NLP. We think it is because RNN can catch the sequence information and CNN is more fit to spatial data. Also, CNN only considers current data, but RNN memorized the previous data, so it can consider the flow of the sentence. In addition to, we could check the effect of BERT and method brings the highest performance. Even applying BERT only, we see that it can result high score. There are some further research topics that we haven't done for this project. We can check the limitation of BERT and improve it, and we can consider another CNN structure and RNN structure. There might be some more suitable structures, so we expect that we can improve the performance. Also, we can apply word embedding methods like word2vec and check the effect of embedding. These are references of our research, and thank you for listening.